Okay, let's do office hours. Office hours. Office hour.
It was fun taking your class.
Thanks. Question. Yeah. So we define P to be deterministic polynomial time. And NP is non-deterministic polytime. So the definitions are in chapter 7 of the book. And we were able to show that NP could, instead of thinking of this non-deterministic polytime thing, we could instead think of it as you're given this magical certificate that you can verify deterministically in polytime. So you're given this certificate C, and the idea is deterministically verify input using C in polytime. So as an example, for CNF set, the problem that we talked about, where we had these clauses and variables, and we wanted to see, is there a way to make the formula true? Well, a certificate in that sense would be, you set this variable to this truth value, you set the second variable to this truth value, etc. And that's just a way, so now we have to verify, was that magical certificate of assignments, does that actually make the formula true or not? So, so you're just given this supposedly advice. Yeah, this is probably your proof that the input really is in this language. So like this formula is satisfiable, but we have to verify that it really is accurate. So like for CNF SAT, it's verifying that the formula really is satisfied by this certificate assignment. Another one that we saw was K-clique, where we wanted to see, is there a subgraph on K vertices that has every edge among those K vertices present? And a certificate there would be the list of K vertices. And then we would just verify among those K vertices, does it really have every single edge present among those K vertices? So it's just a way of verifying quickly that a supposed solution is correct. Okay, does that make sense? Okay. Other questions? Yeah. Any example in mind? Mm-hmm. Mm-hmm. Yep. Okay. Yeah, so I know that one's in the back of the book. In back of chapter 7, sorry. So double sat is formula. So does it say 3 sat or does it say? No. What is the formula? Is it just an arbitrary formula, or is it a CNF formula, or what? Or is it any formula? Okay, so it doesn't matter then. So let's just say Boolean formula. Doesn't have to be in CNF or anything. And has at least 2 satisfying assignments. So this one's actually pretty easy. So can we show that this is an NP? Well, what would be a certificate for me to verify that the formula really does have at least two satisfying assignments? How about 2 lists of assignments? So the certificate B is 2 sets of assignments to verify except if and only if both assignments both assignments satisfy the formula. So instead of normal SAT or CNF SAT or whatever, where a certificate would be a single assignment, and then you just verify, is that assignment really a satisfying one? Here, we need 2 of them, because even if there is some satisfying assignment, there might not be another one. So if we're given 2 and we verify, yeah, both of them really do satisfy, then we can say, yeah, the formula does have at least 2 satisfying assignments. Okay? Well, if I want to show it's NP complete, what else do I need to do? NP hard. Well, let's see. So now we got to pick what problem, NP complete problem, we should reduce to double SAT. So we got to get some input in some other problem we'll pick, and we got to transform it into a formula that has at least 2 satisfying assignments. Okay? Well, what's a problem that seems really close to double SAT? Well, how about another SAT problem? CNF SAT, 3 SAT, all of them work. So how about let's reduce CNF SAT to double SAT. So there are many ways you can do this one, but let's see. We got to be given a CNF formula, phi, let's say, and we got to transform it into, let's say, phi prime that has 2 SAT assignments, or at least 2 satisfying assignments, if and only if phi, the original one, was satisfiable. Okay, so if the original formula was not satisfiable, we better have at most 2 satisfying at most 1 satisfying assignment, or 0. And if the original one was satisfiable, we got to have at least 2 in the formula that we make at the end. Okay. Well, suppose it does have a satisfying assignment. Well, how do we make it so that it has at least 2? Maybe it only has 1. Well, how about let's just add another clause on top of it that gives you 2 at least different assignments. So let's consider phi, the formula originally, and x or y, where x and y are new variables. This actually does at least 3 satisfying assignments, but that's not important here, as long as it's at least 2. Well, let's see. Suppose phi itself has a satisfying assignment. How many does this one have, at least? Well, how many ways can I satisfy that single clause by itself? It's not a rhetorical question. 3, right? I can't set x to be false and y to be false. But as long as at least one or both of them are, then we're good. So if there's one satisfying assignment in phi, then I have at least 3 here. Because for each one of those 3, I can have the satisfying assignment I originally had. Okay? Well, now suppose phi is not satisfiable at all. Is this satisfiable? Well, there's no way to make the clauses or whatever in phi to be true. Could I and it with something to make it become true? No. Something that's false and anything can never ever be true. So this construction is correct. So if phi was satisfiable, let's call this phi prime, then phi prime has at least, we actually ended up with 3 satisfying assignments. But as long as it's at least 2, we don't care. Well, if phi was not satisfiable, then we note that if I and it with anything, it can't ever become true. So phi prime is also unsatisfiable because x and y are new variables. Okay, so this kind of idea where you're adding an additional clause to get you at least some number of assignments or yeah, that sort of thing. Yeah, so you always try to add additional clauses here. So we're trying to modify the original formula that it has at least some number of assignments. Well, even if phi originally had at least 2 satisfying assignments, I'm still going to have at least 2 here because I'm only adding 1 clause with new variables in it. So it's not going to change anything. Okay? Any questions about, oh, one more thing. What should we check about this? Well, not finite. Can this reduction take an exponential amount of time? No. What do I have to guarantee about this? That it runs in how much time? Polynomial time. So does this take polynomial time? Yeah. We're only adding a constant number of things at the end. So therefore, it's always polynomial. So we're good. Okay? So that shows it's NP hard, and we showed it was an NP, so therefore it's NP complete. Okay. Other questions? Yeah.
To show that it's NP hard, shows what exactly?
It shows that if this problem happened to be polynomial time solvable, then everything in NP is polynomial time solvable. That's the notion of NP hard, because that NP hard was defined to be every language in NP reduces to this one. So if I wanted to solve everything in NP in poly time, if I have this one, what you do is just do the polynomial time transformation into this one, solve it over here. Because the answer of whether phi prime was satisfiable, has at least 2 sat assignments, is the same as the original, whether it was satisfiable or not. So that it's answer preserving. Yeah. Other questions? Mm-hmm.
Is the deciders and the organizer are Turing machine?
Mm-hmm.
Okay.
Yep. They have different properties in general, but they are Turing machines. Yep.
I see you mentioned like non-deterministic Turing machine
Mm-hmm.
and Turing machine. What's the difference?
There isn't because in terms of what they can compute, we're able to convert a non-deterministic machine into a deterministic one. But I'm not sure what the question is. Sorry.
What means the difference between non-deterministic Turing machine and deterministic?
Yeah, so instead of having exactly one transition to do, you may have many. So just like NFS, the idea is the same. Yeah. Other questions? Yeah.
Could your research be on the exam? Maybe, maybe not. Okay.
We'll find out. But in terms of knowing like the density method or whatever, no. But like something that's applicable to this, like what you've learned in this class, it's possible. So it's not like specifically about that, it's applying it to the material that we've seen. So it won't be like produce a perfect hash family with 6 rows, 12 columns, or whatever. No, but it may or may not be on the test in terms of applying it to this. So like show that this problem about covering arrays is decidable or whatever. And I would define it on the test if it's on the test. Okay. Other questions? I mean, we can cut it early unless there are other questions. Want to cut it early then? Okay, let's cut it early then.